Okay, welcome to IIT Bombay Virtual Competitive Algebra Seminar. We are very happy to have Jonathan Montano from New Mexico State University for the seminar today. Jonathan works on many aspects of multiplicity theory and several other topics. He graduated from Purdue and then spent time at University of Kansas. And now he is a faculty at New Mexico State University. And he will speak on mixed multiplicities of ideals. This is the first of the two talks. The second talk will be given next week by Aaron Sid Ruiz, his co-author. So, Jonathan, you are welcome to begin.
Right. Thank you, Jugal, for the introduction, and thank you, Jugal and Creative, for the invitation. I am very happy to be talking about this topic that is very close to the research of Jugal. He has done many things on around these ideas. Okay, so let me begin. So as Jugal mentioned, this is joint work with Aaron Sid Ruiz from Ghent University. So let me begin with the setting. All right, so for most of the talk, we are always going to assume that R is a local complete domain. And I will mention when we can assume something more general, but for most of the things that I'm going to be saying, this is the assumption. And the dimension of R, I'm going to denote it by D as usual. So this is always going to be the dimension. And let me begin with the in-primary case. So let's take some in-primary ideals. Right, so S in-primary ideals. So it is very classical that if you compute the length of R modulo I1 to the N1, IS to the NS, then for the vector n big enough, and when I say vector big enough, I mean each component big enough, not just the sum or anything, just each component. This is going to be equal to a polynomial of degree d. And so this is for vectors d that add up to less than or equal to d. And then certain numbers. A1 S or d factorial. D factorial here just means the product of the factorials of the components times n to the d. Okay, and with this I denoted the usual n1 to the d1, n2 to the d2, and so on. Now this is a very classical result, and it has appeared in several ways in different works, but I think it's commonly attributed to Bhattacharya. And this was done in 1957. And then from this polynomial, so this is like a multi-ideal version of the classical Hilbert-Sumner function and Hilbert-Sumner multiplicity. And then if you collect the coefficients in the highest degree, then those are called the mixed multiplicities of the ideals. So the numbers ET of I1 through EAS for vectors that are up to D, so the highest degree of this polynomial. These are called the mixed multiplicities of ideals, and these are non-negative integers. Okay. Now, these numbers have been used by many authors in a variety of contexts and a variety of applications. So let me just mention a few of them just to highlight how important these numbers are. So this was used in the context of integral dependence. As a numerical characterization of joint reductions. And this work was done by Rees, 84, and by Swanson, 93. Okay. This number were also used to find an algebraic interpretation of mixed volumes of polytopes. And this is work of Trung and Verma in 2007. And they were also used by Tessier back in 73. As an algebraic interpretation of minor numbers of complex analytic hypersurfaces. And this is just to highlight some of them. Okay? There has been other applications that I will not mention right now. Now, this is usually how these numbers are defined, just by looking at this polynomial, this multivariate polynomial corresponding to the length of this products of ideals. But for our purposes, I'm gonna write a slightly different way to define these numbers. And what I'm gonna do is, so let me call this formula star. So what I'm gonna do is I'm gonna multiply by a variable m here, and I'm gonna divide by m to the d. So what does that? If you take the limit when n goes to infinity, it is that it deletes the lower degree terms and just end up with the degree d term. So from a star, what you obtain is the following. That the limit when m goes to infinity of the length of r modulo I1 to the n1 times m, is and s times m divided by m to the d. Okay, just take the limit, lower degree terms disappear, and you're done with the highest degree term in degree d. So this is equal to sum for the d's that add up to exactly d of these coefficients for d factorial n to the d. Okay, and this holds for any n, not just high enough. Okay. Now, so this is the way we're gonna interpret or think about Hilbert functions. Okay, it's just by taking these corresponding limits, right? So yeah, so this is how we're going to be able to extend this definition of mixed multiplicities to the context of graded families, not just for ideals. All right, so as I said, this talk is about graded families. So I need to mention first what graded families of ideals. And this is becoming a more common concept, but if you have never seen it, let me remind you what that is. Okay. All right, so we say that a sequence of ideals is a graded family if the following holds. So we need the first ideal I0 to be the ring, and then for any n and m, im times im sits inside in plus m. Okay, for n. Now, clearly, this condition is really mild, and so this type of example of graded families are everywhere. Okay, just to mention a few familiar graded families, we can see besides the usual powers of ideals, we have symbolic powers. We have integral closure powers. We have rational powers, which are like a refinement of integral closures. We have ideal corresponding to valuations. Etc. Now, if you impose the extra condition that in plus 1 is inside in for every n, okay, so notice that in most of these examples, this is what happens. So in this case, I is called a filtration. Okay. So the first step, and it was a major step, but the first step towards defining mixed multiplicities of graded families was done by Kotkowski, Sarkar, and Srinivasan. In 2019, and what they did was they defined mixed multiplicities of filtrations. And they use these numbers to find certain applications corresponding to to this type of filtrations over here. In particular, they apply this in the setting of integral closures. Right. Now, it is important to mention that even though this is a major step towards defining a more general type of mixed multiplicities, they really need the assumption that the graded families are filtrations. Okay, so this work started because my co-author and me wanted to see if we could define this type of mixed multiplicities for general types of graded families. All right, so for the next result, I'm going to assume that we have several graded families, not just filtrations, okay? All right, so what we need here is we want I1 and IS to be arbitrary graded families. Of ideals. So the first main result here, and once again, this is joint work with Jaron Citrus. Is the following. So keep in mind this definition of mixed multiplicities by taking the limit, so multiplying by this m and taking the limit, and this is how you recover this. You define these mixed multiplicities here. So now using this type of limits, but instead of taking powers of ideals, we take the graded families, we obtain the following. So the limit when m goes to infinity of the length of r modulo I1 m and 1. So notice that here, instead of taking I to the m and 1, we're taking I sub m and 1 because these are graded families through is m and s divided by m to the d. What we show is that this is a homogeneous polynomial of degree d. And if we write down exactly how it looks like, so it looks like this. Then these numbers here is what we're going to take as the definition of mixed multiplicity. Okay, and then before they were non-negative integers, now they could be just real numbers, okay? not just integers. I mean, they cannot be integers. There are examples where these numbers are not integers. So the definition is that the numbers in highest degree these are real numbers, and they are the mixed multiplicities of the graded families. All right, so I am not going to mention much about the proof, but I do want to mention the main ingredient, okay? And the main ingredient to prove this is another limit, okay? And it's the following. So the double limit p to infinity, m to infinity of the following lengths So I'm going to slow down a little bit here to make it clear what are the powers that we are taking now. So what we do is, for each P, what we're going to do is we're going to take the first graded family, we take the pth ideal there, and raise it to the n times n1. And then we do the same with the others. So now we need to divide this by p to the d, n to the d. So it turns out that this limit, this double limit, is equal to the single limit that we considered before. I1, Mn1, Is, Mns, n to the d. Now, notice that since here we are taking just regular powers of certain ideals, then for a fixed p, this limit here is a homogeneous polynomial of degree d. So what we have is that when we take the limit when p goes to infinity, this is a limit of homogeneous polynomials, which goes to a homogeneous polynomial of degree d, and which coincides with this limit over here. Now, this double limit here, this double limit result, only allows us to prove our main result, but it also gives us the following interesting consequence. So the limit when p goes to infinity of the mixed multiplicities of the ideals I1p through ISP, p to the d. So notice that here, these numbers are just mixed multiplicities of ideals, like in the classical setting. And this limit coincides with our new numbers. So the mixed multiplicities of the graded families. Okay. Now, this type of limits have been considered before, not in the context of mixed multiplicities, but just regular multiplicities. And it's usually referred to in the literature as the volume equal multiplicity formula. So you can think of this as like a mixed version of the volume equal multiplicity formula. Now this volume equal multiplicity formula has appeared in many works. For example, Ein Lazarsfeld-Smith in 2003 for ideals corresponding to Avianca evaluations. Mustatsa for in the regular equicharacteristic case. Lazarsfeld and Mustatsa in 2009 for local domains that are essentially of finite type over algebraic closed fields. And finally, Kotkowski in 2015 obtained this general volume equal multiplicity formula under the mild assumption that the near radical of the completion doesn't have maximal dimension. All right, so this is what I wanted to say in primary case. Another important part of our work is that we are able to define mixed multiplicities in a more general context where only one of the filtrations, or sorry, one of the graded families is assumed to be in primary. Okay. So I'm gonna start by defining this other type of mixed multiplicities in the classical case of powers of ideas. So it's gonna look a little bit like repetition, but I want to make it clear to highlight the differences between the two. All right. So in the classical definition of mixed multiplicities, we are going to take only one ideal to be in primary, and the other ones are just ideals of positive grade. So J1 through JR, ideals of positive grade. All right, so the length of J1 to the N1, JR to the NR over I to the N0 plus 1, or let me just write N0, J1 to the N1, JR to the NR. This length, for n big enough, also coincide with a polynomial of degree d. Okay, and here we need this vectors d of degree at most d, and the d0 to be positive, and it looks similar like in the primary case, but this guy is a little different because it's in primary. So what we say is that these are mixed multiplicities of the other ideals with respect to I. Right. Now, as we did before, you can also multiply by an m here and divide by m to the d and take the limit. And what does that is that it deletes or it removes all the lower terms of this polynomial. So that's the approach we're going to take here as well. All right, so now what we need is a graded family that is in primary. So this guy here is in primary. And we need others that are not necessarily in primary. Okay. And these are graded families. All right. Now we need an extra assumption here, and this is a technical assumption that has been also considered in the past in this type of ideas. And without this assumption, there is not much you can do. And so let me define what the assumption is. So the definition. We say that the graded families I, J1 through the JS as before, satisfy linear growth if there exists a C in N such that the following holds. So J1 P to the N 1 J R P. Let me. I think I changed from R to S at some point. Let me just stick with R. So to the N S. The intersection of this product with the maximal ideal to the C times P times M, and this is probably not the best notation because I'm writing M and M. I don't know how to fix that, but let's say CPT, that this intersection is equal to similar intersection but multiplying with the ideal IP to the M to the N0. CPT, and this for every N, P, and T. Okay. Now this looks like a rather strong condition, and it kind of is, but it is satisfied by a large amount of graded families. So let me just, since this is an assumption we need for the theorem, let me just tell you some examples of when this holds. Now, of course, this holds for in primary graded families, but this case is not interesting for the second result because it was covered before. But the in primary graded families satisfy this. Now, in the graded case, it also holds if, so linear growth holds if there is a bound, a linear bound for the degrees of generators of the graded families J1 through JS. I mean, in particular, since graded families are, it seems, degree of generators are bounded by regularity, in particular, this holds if there is a linear bound for regularity, which is a condition that has been studied a lot before. For instance, this bound on this linear bound degrees of generators happen for symbolic powers of ideals of dimension at most 2. And this is a result by Chandler in 97. It also holds for initial ideals of dimension at most 1. And this was proved by Herzog, Hoa, and Trung in 2002. It holds if the ring, like the blow-up algebra, like the Risk type of algebra, direct sum in t to the n inside R join t. If this is Noetherian, for instance, this happens if you take symbolic powers of monomial ideals or symbolic powers of determinantal ideals, and so on. And finally, another example is that it holds for monomial ideals corresponding to cones over convex bodies. And is this example what allows us to apply these results to mixed volumes of convex bodies? And this can be seen as a generalization of the work of Trung and Verma from polytopes to arbitrary convex bodies. And this is the topic of next week's talk by Jaron. Mixed volume of convex bodies. Okay, and I'm advertising next week's talk. All right, so let me now, sorry, my laptop is gonna die, so I need to plug it in. Right. All right, so the next result is the following. So here, it's also joint work with Jaron. All right, so we're gonna take creative families I, J1, JR as before, particular satisfying a linear growth. And of course, this one here is in primary. Right, so now what we prove is that the limit when m goes to infinity of the length of J1, Mn1, JR, Mn over I sub Mn0, J1, Mn1, JS, Mns over m to the d. This is a polynomial of degree d. And this is equal to sum for this equal to d and d0 bigger than 0 of similar polynomial as before. And clearly from here we can define the mixed multiplicities in this more general setting. Now, the numbers ED, I, J1 through JR. These are, again, non-negative real numbers. And these are the mixed multiplicities of the graded families I, J1 through the JR. All right, so this is pretty much what we obtained in this work. So I want to use the remaining time, or at least some of it, to tell you some further properties of these numbers. All right, so mostly in the primary case. Right, so, and here, so we're gonna, so in this primary case. So we're gonna take some graded families. That are in primary. Okay. Now, if you look at these numbers here, I mean, the only assumption we had was that this graded family satisfied linear growth. And I mentioned before that this is automatically satisfied in a primary case. So we have two types of numbers, right? The numbers that we obtained in the previous result here, from here. But we also have now a new type of results, type of numbers obtained from this result. Okay, so a natural question is, how do they relate? So the first property I want to mention is the following. So let D be the vector D1 through DR. Now, if this 0 is equal to 0, then the multiplicity D0 D of these graded families so if this is 0, then you can just delete the first guy. So this is E, D, J1 through JR. Now, this is kind of expected, right? But if this 0 is not 0, what we have is the following. That E, D0, D of J1 to JR is equal to the corresponding mixed multiplicity in corresponding to the second result. All right. So if you're familiar with the ideas surrounding multiplicities, you know that we're usually interested in what happens with respect to additivity on short stack sequences. So we do have a result related to that. Let me just first mention, and I'm not going to write much about that, but you can define the mixed multiplicities corresponding to a module. Instead of taking, R here, you take the module M, and then here the product of ideas times M, and you obtain the mixed multiplicity corresponding to the module. So the second property that we obtain is the following. If you take a sure exact sequence, M prime to M double prime to 0, then these numbers are additive. So ED M J1 through JR is equal to the sum of the other two. And we can use this additivity to obtain the following additivity formula for mixed multiplicities, which is ED of M J1 to JR is equal to the sum of P in the spectrum of the length of RP times MP RP of MP times the mixed multiplicity over R modulo P of the extension of the filtrations of degraded families on the quotients. So J1 extended to R mod P, JR extended to R mod P. And this sum runs over P such that the dimension of R mod P is maximal. Okay, so this is like a additive formula for mixed multiplicities of graded families. All right, so I think I'm going to stop here.
Thank you, Jonathan. We will take some questions now. You can unmute and ask questions.
Jonathan, I have a question.
Yes.
Yeah. Was there a specific reason to assume that the ring is a domain in the beginning?
Yeah. So the idea that we use for the proofs is these ideas of Newton groups of bodies, as it was used by Topolsky and co-authors, and for those ideas you do need local complete domain, because that's only in that setting you can define certain valuations that allow you to split portions of ideals, of R module ideals, as sums of points in certain semigroups, elements of certain semigroups. So it's just because of the method that we use. The methods make local complete domain.
Thanks.
Yeah, Jonathan, I have a question.
Yeah.
Since the setting is very general, it applies to symbolic powers and other filtrations. Are there any concrete applications to the filtration of symbolic powers when the restring is not Noetherian?
That's a good question. So we haven't particularly, you know, tried to find applications in that setting, but it's something that can be done here, right? It's
Yeah.
definitely something that it could be done and see what those numbers are. So
So,
the
so
short
these
answer is
numbers
that
are,
we don't have applications so far, but it is a reasonable next step.
yeah, I mean, it'll be nice to understand what these numbers are for, say, a height 2 prime in a
Exactly.
three-dimensional local ring,
Yeah.
or
Exactly. Yeah.
monomial primes, because in many situations the restring is not Noetherian for those monomial
Correct.
primes. So whether
Correct.
these numbers give any information on the symbolic Greece algebra.
Exactly. Yeah. That's a very very good point.
Yeah, and these more general mixed multiplicities that you consider when the filtrations are not M primary, except for one. So in that case, do we have analogs of Minkowski inequalities?
Yeah. So I didn't. Actually, we do have those type of inequalities, but in the primary case, actually.
So non-M primary case, do you expect
It
something?
no, I don't think we have in that setting. No.
Mhm.
Yeah. Do they hold for the regular powers? I'm not sure.
Yes, that's
Yes.
proved in Katkowski, Sarkar, Srinivasan's paper. There are
But
several versions of Minkowski inequalities proved there.
but their paper isn't. I think it's in the primary case.
Yeah, that is in M primary. Yeah. So my question is, if you take non-M primary case, then do we have the Minkowski type inequalities?
We do not have that. No.
Because for mixed volumes of polytopes, we do have the inequalities which look similar to Minkowski inequalities, and the mixed volumes of polytopes arise in the non-M primary situation. So it is natural to expect that even the non-M primary case, the Minkowski inequality could be true, so that you could prove these for mixed volumes algebraically.
Yeah. Yeah. So I want to say that whatever type of inequalities hold for regular powers is going to hold for our numbers, just because we have this volume equal multiplicity formula. So you take limits and then you take the same type of inequalities.
Uh-huh.
Yeah, but and you're right. I mean, if as Jairo is going to talk about next week, for certain graded families, monomial graded families corresponding to cones of convex lattice, you can reinterpret these numbers as mixed volumes of convex lattice. So whatever happens in the combinatorial setting of complex lattice is also going to happen for those numbers. But that's just a specific setting.
Okay.
But thank you. That's a good question. But we do have several versions of Minkowski inequalities in the primary case, and I didn't mention it today just because of time, but
Yeah.
we do have
Okay.
some of them.
Okay. Thank you.
Yeah. Thank you for the question.
Yeah. Any other questions? Yeah, I suppose there are no questions. So we will meet next week for the next talk in this series, where we will see the connections with convex geometry, how these algebraic ideas make sense in convex geometry. And so we will all meet next week. Thank you.
Thank you again for the invitation and for everybody
Thank
for
you.
coming.